In this section, I'll show you the shape of a ratio level histogram and the names of the shapes. A mathematically uniform distribution has a perfectly flat top, as seen here. The top of the distribution is perfectly flat because this is a list of 10 zeros, 10 ones, 10 twos, 10 threes, all the way across to 10 nines. And so there's 10 of each. See, it's on the y-axis there, sorry. And since there's 10 of each number, each column is of equal height. That's a mathematically uniform distribution. Distributions are not usually mathematically uniform, not in the world of statistics. More often we get things that are roughly uniform. We still call them a uniform distribution. This is a roughly uniform distribution. This is actually also the numbers from 0 to 9.99, and they are evenly distributed from 0 to 9.99. We once again have 10 columns, but you'll notice we don't have exactly 10 of each. We have 9, 10, 12. The number varies by 1 or 2 up or down, but the distribution is still considered roughly uniform. There are roughly 10 in each column, give or take 1 or 2. It's not perfectly flat, but it's still considered uniform. That's in contrast to a centrally peaked, roughly symmetric uniform. Here we can see a roughly peaked, centrally peaked, roughly symmetric. That means it's symmetric, what we call bilaterally. It's left-right symmetric. On the left and the right, it's symmetric. And so there's my left-right symmetric. The middle of the peak is the tallest. The middle of the distribution is the tallest peak. And this middle is where the mode, the median, and the mean will be found, between 4.2 and 4.5 on this particular histogram. There's a left side and a right side. It kind of looks like a hill, maybe a little bit like a bell. So it's sometimes called the bell curve. It's also referred to in statistics as the normal curve, because this is what we normally get when we have random distribution away from a central mean. That is our data is randomly distributed around a central mean. You see this in human heart rates. You see this in all sorts of situations. And it's considered in some fields to be a desirable shape. For example, in education, a test is considered to be quote-unquote well-behaved if it generates a roughly normal distribution. That means you've really tested something. If it's highly skewed, which we'll see later, that may mean that you didn't test anything or didn't test what you thought you were testing. Another distribution is the bimodal distribution. The bimodal distribution will look like a bimodal. It'll have two modes. Bimodal means there's two modes. In other words, you can see that in the left and right peak here. So we've got a bimodal histogram distribution. Maybe give it another color and turn off the legend so we can see the distribution a little bit better. There's our bimodal distribution. There'll be two modes, one on the right peak, one on the left peak. Bimodal distributions may indicate that you have two different populations in your sample. And the other thing they show you is that your mode and your median, well, there'll be two modes, or there could be two modes, but the mean and the median will be in the middle where there's very few data. So citing the mean or the median won't have much meaning. Bimodal distributions have sometimes happened in my math classes. I get a bimodal distribution when half of the class is completely lost and half of the class is understanding the material. The one half is lost and has no idea what's happening in the class, and the other half is doing all right in the class. They're behaving, as we say, behaving in a manner as would be expected. That makes it very difficult, because if I teach to the one peak, to the students who are understanding, they're doing fine, but the lost students stay lost. If I pitch it lower to the students who are lost, well, the students who are doing fine are now bored. So that's always a difficult one. And so we sometimes think of bimodal as being a sign that maybe something is behaving differently than we think it, than we normally, that shape, think it should behave. We saw the leaflets a little earlier. The leaflets made a distribution. Here you'll see I don't have a histogram. I have a couple options to get a histogram, here or here. Either one will get me a histogram. There's my histogram. And I'll go ahead and turn off the legend. I've been doing that. And these are leaves. So we'll go back and change that color to be a leaf color. This is Senna alata, which has a dark green leaf. So we'll go ahead and let that match, just to make it match the fact that it's a plant. And we can see here that most of the leaflets are between 11 and 12.5 centimeters, and there's a few that are smaller. By a few, I mean we've got 11 leaflets at this between 11 and 12.5. You see that over here. But down here, there's only 3, 3, 3, and just 2 leaflets down here. So the distribution is not symmetric, it's not uniform, it's not bimodal. There is just this one mode over here, so to speak, but there's this tail stretching out to the left. We refer to this as a skewed left distribution. When it's skewed left, it means most of the data is on the right side. It's a little bit counterintuitive, but that's the way it works. If it's skewed right, the tail is on the right side. The tail are unusual values. In this case, the mode and the median will probably be somewhere in this upper class, bucket, bin, or interval. And the mean will be somewhere down here. The mean will be somewhere partway down. The tail will pull the mean down. In this case, the median and the mode are better descriptions of the middle. When you have a symmetric distribution, the mean is a good description of the middle. But in this case, the mean doesn't well describe the middle. The median will do a better job of it. So the shape can tell us what statistics we should be using. And marble masses, these are just marbles. I once again get a line chart. I don't want that. But let me scroll down and use the other histogram. They're the same. It doesn't matter which icon you use. Those are both histograms. And I've got a centrally peaked, roughly symmetric distribution. This is roughly symmetric. We can see here that most of the marbles are between 5 and 5.33 grams. There's a few marbles above 5.33 and a few above 5. There may be a tiny bit of a leftish tail, but that may also be due to these bucket breakpoints, and those we can't control in the app. Now, in a more advanced class, you'll want to control the bucket breakage points here, these numbers on the x-axis. You'll also want to control the number of buckets or bins or classes. This has actually got 6, including 2 blank ones in there. So, put it back there. You remember the undo button when you do things you didn't mean to do. In a more advanced class, we'll want to control those. But in introductory statistics, just getting a feel for this shape will be fine. And there were 36 marbles, so Google went for 6 buckets. But when it went to set up the x-axis, it just set it from 4 to 6, and so it wound up with a couple empty buckets. That's slightly suboptimal, but it still tells us what we need to know, that the distribution is centrally peaked, roughly symmetric. It's basically a normal distribution, and so the size of the marbles is varying randomly around the mean. And that will be good enough for an introductory statistics class to let us know that we can use normal frequency-based statistics to make predictions on where the marbles will be distributed at. That's a quick look at the different shapes that you can get: uniform, roughly symmetric, bimodal, skewed, and some of the terminology we use to describe those shapes, and a little bit of how they relate back to the measures of middle. Thank you for watching.